house and output like the price of the house. So the algorithm, as it runs through the model, through epochs in the model, it trains the model to figure out what is happening with the data sets. And after that, they validate the model by taking a different set of data sets with its input and output and making sure that there are error between the input and the expected output and the actual outputs are small to make sure that their model is actually correct. Before they test it, and in testing, they just put in new inputs with no outputs, and then the model essentially predicts what the output should be. So there's an abstraction of what the deep learning process looks like, the supervised learning version of deep learning looks like. So on to our actual program. So I'm going to give you an example, like the simplest version of a deep learning neural network, which is it has an input, runs through a hidden layer, and gives an output. So for example, like I said, when determining the price of a house, let's say you have an input of a house, let's say the size of the house. You run it through the model, which is the hidden layer, and then it gives you the price of the house. But like we all know, you don't just determine the size, the price of a house just by this size. There are so many things that's involved. For example, the zip code. A house in a small house in New York might be more expensive than a big house in a place like Korea. So there are multiple parameters that influence the price of the house. So in all actuality, a neural network looks something like this, where all the inputs are run through the hidden layer to give out an output. You good there? Yeah. So let's take a closer look at what is happening. As it turns out, the inputs are connected to the hidden layer through weights, and the weights are simply a way to determine how much that particular parameter is affecting the output. So for example, is the size of the house more important than, let's say, the zip code? So again, like the example I gave previously, a small house in New York might probably be more expensive than a big house in Korea. That's because the zip code weighs more in this model than like the size of the house. I don't know if that makes sense. Okay, so when you run it through it, it becomes a weighted sum. Like I said, we need to, we weight it because we want to determine whether the weight is how much the weight is affecting, how much the input is affecting the output. Yeah, but like we all know, the real world isn't really all that linear. It's very hard to find linear models in the real world. So after you get that summation, you run it through an activation function, and then that gives you your output. Now, with this forward propagation algorithm, in the days when deep learning the backpropagation algorithm was being brought about, what they wanted to do, the problems they were trying to solve were classification problems. In a sense, if you give the model a picture of a cat, it's able to tell you, hey, this is a picture of a cat, or it's not a picture of a cat. So what they did decide, what the activation function they decided to use was a sigmoid function. So as you can tell, with a sigmoid function, no matter what your inputs are, your outputs are always going to be between 0 and 1. And it's not strictly 0 and 1 like I gave the example, but sometimes the results can be at 0.8. That means there's a high probability that the picture is a cat, or 0.4. That means there's a low probability that the picture is a cat, or it's a slide. So I'm just repeating this equation again. So the initial input, which we run through the activation function, is simply a product of the input xi times the weight. Yeah. And then the activation function we use in this backpropagation algorithm is the sigmoid function. Why? Because we need to make sure that all the outputs are between 0 and 1 because of classification problems with what they're used to. So, yeah. As it turns out, models were not all that accurate. So whenever you train the model and you validate the model, sometimes when you test the model, it gives wrong answers. For example, if you put in a 4-bedroom house in Korea, and then your model gives you an answer like $12 million. That is clearly wrong. So, yes. So what happened? Sorry. Okay. So what happened was that this people who came up. So the total error between the actual output, which is the YJ, and then the desired output, which is the DJ, we try to find the difference between them, but we apply the mean squared error. Why? Because we want to make sure that the errors that are larger counts more than the errors that are smaller, and we square it because we want to make it always positive, no matter what. And for this to, for those who know the mean squared error, it's actually 1 out of n, the number of iterations times the summation of yj minus dj all squared. But we are picking 2 as an arbitrary number because whenever we do differentiate, which we'll get to, it cancels out nicely for us. Yeah. So another tangent. For those of us who've taken Calc 3, you probably know gradient descent, but for the rest of us, a gradient descent is simply the first order iterative optimization algorithm for finding the minimum of a function. That's a mouthful. But what it does, the reason it's important is because it's what the model, the backpropagation model algorithm is using to reduce the errors that I showed earlier. So to visualize the gradient descent, let's say you're on the top of a mountain, right, and you want to go down to get to the valley, essentially. You could probably jump and see where you land, or a more efficient way is that you stand in one place, you look around you, figure out which one has the deepest slope, take that, stand there, look around you, figure out which one has the deepest slope, take it all the way till you reach to the bottom of the valley. Yeah. So in 3D formula, this is 3D graphing, this is what it looks like. Yeah. But this might be too complex, so in simple 2D, this is what it looks like. Just level down to hit the bottom. Okay. Yeah. So back to the backpropagation algorithm. Like I said, the backpropagation algorithm is simply a supervised learning procedure that repeatedly adjusts the weights, which are the connections between the network, so as to minimize the difference between the desired output and the actual output. So simply, it is just an algorithm that uses the gradient descent to minimize the cost function or the total error in a model. Why is it important? It's important because it was a fast way to compute the sensitivity of the output of the neural network. In a sense, figuring out how much each input was affecting the output. So like the size of the house and the zip code, how much of it is affecting the price of the house. But most importantly, it was very efficient with thousands of parameters and even millions of parameters. So what I showed you earlier on is called the forward path or the forward propagation. So you put in some inputs, you get an output. So what the backpropagation algorithm is seeking to do is to take that output, pass it through the model again to figure out the weight, by changing the weight to figure out the inputs. Is that clear? Yeah. So again, I want to repeat that the total input is equal to yj times wj. Why? Because we are going this way. So the y's become the input and the x's become the output. And then, again, just a reminder, we use the activation function used in this model is the sigmoid function, which is 1 out of 1 plus e to the minus h, e to the minus hj. Yeah. And the total error, I'm just repeating this so that you get a clear sense of where this is going. Total error is the mean squared error between the desired output, which is dj, and then the actual output, which is yj. So how do you minimize the error with respect to weight? As it turns out, you can minimize that by adjusting the weight, which is simply finding the partial derivative of e with respect to each weight. So what are the error, the error you're looking for is the error between each. So you're trying to adjust each single weight, not the entire weight. So by adjusting each single weight, so with this, the I is just minimizing the error with each single desired output and its actual output. That's why the J's turn into I's. So from that henceforth, you're going to be using I's. Yeah. So one thing that you can see is that this error function has no W's in it. Right? We are trying to differentiate it with respect to Wi, but there's no W in the error function. As it turns out, we can apply some calculus method, the chain rule to this, to figure it out. But what we do know is that we have the variable yi in this error function. So what we can start by doing is by finding the partial derivative of the error with respect to the yi. And simple calculus, it turns out that you bring the two here, it cancels out. Then the partial derivative of e with respect to yi simply becomes yi minus di. Yeah. And then again, we realize that xi is a variable in so it's a variable in yi. So if you want to find the partial derivative of e with respect to xi, we can again apply the chain rule where we can say that the partial derivative of e with respect to xi is equal to the partial derivative of e with respect to yi, which we know, times dyi out of dxi, which we can figure out. So for those of us who've taken, okay, so as it turns out, when you differentiate yi with respect to xi, you get e to the minus xi out of 1 plus e to the minus xi all squared. And then if you apply a bit of algebra, you can just separate it to make it, to simplify it, where you just take out 1 out of 1 plus e to the minus xi times 1 minus 1 out of 1 plus e to the minus xi. Why? Because this is equal to y, and then this essentially becomes dy dxi simply becomes yi times 1 minus yi. So you substitute that into the partial derivative of e with respect to xi, and then you get partial derivative of e with respect to yi times yi to the bracket 1 minus yi. So now that we know the partial derivative of e with respect to yi, we know the partial derivative of e with respect to xi, we can figure out the partial derivative of e with respect to wi using the chain rule again. Again, the xi is equal to yi times wi, and if you apply, if you differentiate xi with respect to wi, you simply get yi, and the partial derivative of e with respect to wi is equal to, again, applying the chain rule, the partial derivative of e with respect to xi times dxi out of gwi, which simply gives you partial derivative of e with respect to xi times yi. Now, if we substitute the xi into the equation, we finally get the partial derivative of e with respect to wi, which is adjusting the weights of to minimize the error function. Simply becomes partial derivative of e with respect to yi times yi multiplied by 1 minus yi times yi. And this is an equation that is utilized especially in deep learning. Again, for those who in computer science, if you look at PyTorch or TensorFlow, there are implementations of this particular equations in the backpropagation algorithm function. So, like I said, the backpropagation algorithm was efficient. However, there are some limitations. Most notably is that it can be slow at converging to the global minimum sometimes. Again, the most important thing is that the gradient descent can get stuck in a local minimum, giving suboptimal results. By that I mean that if you have a function like this, if you apply the gradient descent and then you're starting from this part, you're going to get stuck here. Why? Because when you're here, there's no slope that is close, so it's going to be here. However, as you can see, this becomes a local minimum, where the global minimum exists. And so the error is still large, and it doesn't really solve your model's problems. So there are ways to mitigate this error, and this is simply by changing the activation functions. So I introduced the sigmoid activation functions, which essentially gave outputs between 0 and 1. There are multiple other functions, notably the hyperbolic tangent function, the rectified linear units, and then the leaky rectified linear units, max out and ELU. And depending on what your problem is, the problem you're trying to solve, and what's your error, your total error, you can adjust using these various activation functions to ensure that your errors are getting minimized. In a short sense, will AI take over the